Hello all. I have this old paper. It's a Unit 5 paper from June 2023 lying around. So today I want to do a quick video because I have something else to do today. So I will just try to fly through the questions. So let's dive in and start with section A and question 1. So the ultimate fate of the universe is uncertain. Which of the following would result in an open universe? Okay. Option A, the average density of the universe is equal to the critical density of the universe. That will result in a flat universe. B, the average density of the universe is less than the critical density of the universe. Okay, this is the correct answer because gravity will not be able to pull this back. So B. Okay. Question 2. A hydrogen source on Earth emits a spectral line with a wavelength of 410 nanometers. That's blue, I guess. So an observer determines the wavelength of the same line in the spectrum of a star. The star is moving away from the Earth at 2.5% of the speed of light. What is the wavelength of the line as determined by the observer? So okay, we have the Doppler factor being equal to 0.025, which should be equal to delta lambda over lambda. So the shift is equal to 0.025 times 410 nanometers or 10.25 nanometers, which should be added to this, to 410, because this is moving away, so it's a redshift, so the wavelength shifts towards the red, which is towards 700 nanometers, right? So the correct answer is C. All right, question 3. The distances to stars can be determined using trigonometric parallax. Star X has twice the parallax angle of star Y. Which of the following statements is correct? Okay, it's a little bit of a difficult problem to answer without seeing what's going on. So, okay, that's sun. This is the sun, right? And this is the position of the Earth now and in 6 months, right? And this is 1 astronomical unit, okay? So they are telling us that you have star X and which has some trigonometric parallax. Let's use red. This is the parallax of star X, right? And it's twice the parallax angle of star Y. So this means that Y is further back, right? So this will be star Y, okay? So let's call this theta, okay? So let's go see the options. I hope this makes sense. Okay. So the distance, okay, star X has twice the parallax of star Y. Okay, so this is X, so it should be closer, right? So what's the correct option? A, the distance of star X from Earth is twice the distance of star Y. No. The distance of star X from Earth is 4 times the distance of star Y from Earth. Also incorrect. C, the distance of star Y from Earth is twice the distance of star X from Earth. Okay, this is the correct answer, okay, because you can figure it out by looking at this diagram. Okay, let's go to question 4. A satellite of mass m is on Earth's surface. The satellite is moved into a circular orbit of height h above the Earth. The mass of the Earth is m and the radius of the Earth is r. Which of the following gives the change in gravitational potential energy of the satellite? Okay, so the change is equal to the final gravitational potential energy minus the initial one. Okay, there's something wrong here. Let me see. Wait, I said something wrong. So the change in gravitational potential is delta V. Okay, I'm sorry. I'm sorry if I confused you. So the final gravitational potential is minus g m over the radius of the Earth plus h, and the initial is just g minus of minus gives you plus gm over r. Okay, so the difference in the gravitational potential energy will be m times delta V, okay, where m is the mass of the satellite, okay? So the correct answer is B, okay? And immediately from these answers, you see that option A is actually wrong because that's a change in gravitational potential, not gravitational potential energy. Option C is wrong because that gives you the gravitational field strength, so obviously wrong. And then option D gives you the gravitational force, okay? So actually, I think I went the orthodox way of solving it, okay, using the math and the physics we know. But this is an example of a problem in which you can answer without, just by looking at the answers, okay? I mean, you eliminate everything that is wrong, and you have three obviously wrong answers. So the only correct answer is B in this example. It doesn't always work, but sometimes it does. All right. Moving on to question 5. Measurements related to a distant galaxy may be used to determine the value of the Hubble constant. Which two measurements related to a distant galaxy may be used? Okay, so distance from the Earth and mass. I don't know how that's going to help you. Distance from the Earth and recession velocity. Okay, that actually works, right? Because V, the velocity of a galaxy, is given by the Hubble constant times the distance. And I'm pretty sure this is one of the formulas they actually give you in the back of the paper. Let's go check, I'm sorry. So let's see, is it here? No, is it here? Maybe here. Okay. 4. Okay, unit 5. Astrophysics. Yes. So this is the formula I'm talking about. Okay. So this is also an easy problem, I think, because you can figure it out just by looking at the formulas they give you at the back of the paper. Let's go to question 6. Buildings in earthquake zones often have a structure that includes ductile materials, and I have to add, I have to comment here that I actually live in an area of the world where we have frequent earthquakes, not severe ones. Usually in Cyprus you have earthquakes at the 5 or 6 Richter scale, so it's not terrifying. I mean, this is not Japan, where I think they have earthquakes of 7, maybe 8 Richters or something. So these materials help to dam oscillations of the building during an earthquake. Which of the following describes a ductile material? So a material that behaves elastically under tension kind of sounds promising, but something bothers me. Let's see option B. A material that has a large plastic deformation before it breaks. Okay, that actually works. Because you don't want the building to collapse under an earthquake. Option C says a material that has a large volume of breaking stress. You don't need that. That's useful for pressure, okay? Here we are talking about oscillations. So a material that has a large value of the Young modulus, that doesn't really help. So let's move to question 7. A student is investigating the absorption of gamma radiation by lead. Before starting the investigation, she determines the background count. Which of the following does not affect the background count? The count time, that will affect it, right? The location, that will affect it actually. And in one of my videos, I think I mentioned it, in basements. Okay, so bricks that we use to build buildings, sometimes contain uranium, okay? And when uranium decays, some of the isotopes of uranium decay down to radon, which is a gas. It's an inert gas, which is also radioactive, okay? And because it's really heavy, it sinks to the bottom of houses. So houses that have basements might have radon, okay? So if you count the background radiation there, it's going to be higher than measuring the radiation outside of a building and so on. So the location is actually important. The temperature doesn't affect radioactive decay. So actually that's the answer, but also let's read option D. The type of detector affects the experiment, right? Because some detectors are more sensitive, right? So, question 8. Mars has approximately 8 times the mass of the Moon. Mars has twice the diameter of the Moon. The value of G on the surface of the Moon is 1.6 newtons per kilogram. What is the value of G on the surface of Mars? Let me move to a clean page. So let's just write down, okay, so the field strength on Mars over the field strength on the Moon should be equal to this ratio. So we will have the field strength of Mars will be G times the mass of Mars over the radius of Mars squared, right? And then we will have G mass of the Moon over the radius of the Moon squared. Okay, so G goes away. That's a nice cancellation. So we have M of the Moon of Mars over M of the Moon. Excuse me. Okay, recording. So we'll have mass of the Moon over, mass of Mars. Mass of Mars over the mass of the Moon times the radius of the Moon over the radius of Mars squared. Okay, so they tell you that the mass of the Moon is of Mars is 8 times the mass of the Moon, so we're just left with 8. And then we have to recall that the radius, the ratio of the radii is equal to the ratio of the diameters, right? And they tell us that where is it? Question 8, I'm sorry. Mars has twice the diameter of the Moon, so we have 1/4, because we have 1/2 squared, which gives you 1/4, so 2. Okay, so the correct answer is C, because 2 times 1.6 is 3.2 newtons per kilogram. So on Mars, your mass will be 1/3 of your mass here on Earth, which is crazy. Okay. 2 gas cylinders have the same volume. This is question 9. One cylinder contains nitrogen gas, the other cylinder contains oxygen gas. Both gases are at the same temperature and pressure. Which of the following statements is not correct? Okay, let's write the ideal gas equation. So PV is NKT, okay. Okay. Option A, each cylinder contains the same number of molecules. That's not necessarily, is not correct. 2 gas cylinders have the same volume. One cylinder contains nitrogen and the other contains oxygen. Both gases are at the same temperature and pressure. Okay. So the number of molecules is actually the same. Okay. Then B, the average molecular kinetic energy is the same for each gas. Yes, because the kinetic energy is 3/2 kT, right? It's independent of the mass, okay? C, the density of gas is the same. No, that's wrong. Okay, because they have different masses. And then B, the internal kinetic energy, the internal energy is the same for each gas. That's actually true, okay? Because you have the same number of molecules and the same temperature. And the internal energy is equal to the number of particles times 3/2 kT. Okay. Okay, moving on to question 10. A particle is undergoing simple harmonic motion. The graph shows how the velocity v varies with time for the particle. Which of the following graphs shows how the displacement x varies with t during the same time interval? So in my latest videos, I just work with the equation. So for the velocity, you immediately see that you can see that, okay, you have to have omega a up front. And then what do we see here? What kind of function is this? It's a sine function, right? How do we know this? Because at time 0, particle is at 0 and then it speeds up, okay? So what would x look like? So x is going to be a, we don't know the sign. We will actually in a moment. So, and it's definitely going to be a cosine function, right? But v is the first derivative of x with respect to time. The derivative of cosine is minus sine, okay? But we see that the velocity should have a positive sign, so x is minus a cos omega t, okay? So we can immediately eliminate options A and C, and then also option D, because x starts as positive at time 0. So the correct answer is B. All right, so moving on to question 11. A nucleus of rhenium 187 decays to a nucleus of osmium by emitting a beta minus particle. Complete the nuclear equation for the decay of rhenium 187. All right, so beta decay does not change the mass number, okay? So this is a key result to remember, okay? Beta particles have no mass number. They only have a negative -1 charge, right? So what do we need to balance the equation? We have 75 on the left-hand side. So we need 76 -1, 75. So the left-hand side matches the right-hand side, okay? Part B, the energy released in the decay is 2.6 keVs. You may assume that in this case, the beta particle receives all the emitted energy. Calculate the speed of a beta particle emitted in this decay. Okay, so we will just set 1/2 mv squared equal to 2.6 keVs, right? Right, okay. And this is the mass of an electron, okay? So we have, we can solve for V. V is the square root of 2, okay, times 2.6. 1 keV is 1000 EVs, and 1 EV is 1.6 times 10 to the negative 19 joules, right? Because you have to convert to joules. And then we have to divide this whole thing with the mass of one electron, which is 9.11 times 10 to the negative 31 kilograms. And if we carry on the calculation, we find 3.02 times 10 to the 7 meters per second, which is the answer. All right. Question 12. An airbag is a safety feature used in cars. Okay. Nitrogen gas is released into an airbag. The airbag inflates to a volume of 7.08 times 10 to the negative 2 cubic meters. The pressure of gas in the inflated airbag is 1.24 times 10 to the 5 pascals. Show that the number of molecules of nitrogen gas released into the airbag is about 2 times 10 to the 24. And they give you the temperature of gas in the airbag. Okay, so this is a simple application of the ideal gas law. So PV is NKT. And we are interested in the number of molecules. So N is P times V, pressure times volume, over KT. And we need to plug in all these numbers. guys. Don't forget, okay, I actually need to do it because for some reason I forgot. So just to make sure that I am finding the correct result, because okay, here in my notes I just quote the final result. So let's see. So the pressure is 1.24 times 10 to the 5. Volume is 708 times 10 to the negative 2. K is 1.38 times 10 to the negative 23. And then temperature you have to convert to Kelvin. Never forget that. So 273 plus 25, what's that? 273 plus 25, 298. Okay, let me verify the result. Okay, I have to type numbers in my calculator. Just be patient, guys. I'm sorry. Okay. You don't have to blindly trust yourself, guys, okay? Because I just wrote the result there. So, okay, I found 2.13 times 10 to the 24. Okay, which is about 2 times 10 to the 24 as requested. Okay, that's good. Let's do part B. Nitrogen gas escapes from small holes in the inflated airbag. The pressure decreases to 3.45 times 10 to the 4 pascals. Calculate the number of nitrogen molecules that escape from the airbag. The volume and temperature remain constant. Okay, so the new number of particles in the airbag, okay, should be, I'm just going to copy this equation, so should be PV over KT, okay? Let's switch back to plug. And now the pressure is 3.45 times 10 to the 4, right? The volume is the same, so 708 times 10 to the negative 2. Temperature is the same, so 1.38 times 10 to the minus 23 times 298 yields, okay, let's do the calculation again. 5.94 times 10 to the 23rd. Are we done? No, we have to find how many particles escape, which is just a subtraction between the initial number of molecules minus the final, right? So we find 1.53 times 10 to the 24. That's quite a few molecules escaping. Okay. Let's move to the next question. Okay. A cloud chamber is used to show the tracks of alpha particles and beta particles. These particles ionize the air as they pass through the chamber. Liquid droplets form around the ions. The droplets form visible tracks as shown. Okay, a student makes the following observations. The alpha particle tracks are thick and straight. The beta particle tracks are thin and twisted. Explain these observations. So alpha particles have twice an electron charge, okay, 2e charge. Therefore, they have the thickest lines, okay, because they charge, they ionize many particles, okay. They ionize lots of particles. They are also massive, okay. Alpha particles are massive. Therefore, they are not deflected by much. They they are not deflected much, hence they have straight lines. Okay, and on the other hand, Vita particles are light, so they have twisted tracks, which are thin, as they only have 1 unit of charge. Okay, and that's the answer. Question 14. Ice cubes can be made in an ice cube tray. One type of ice cube tray shown below. Okay. Each compartment in the ice cube tray has dimensions 2.5 by 2.5 by 3.5 centimeters as shown. Show that the mass of water needed to fill one compartment is about 0.02 kilograms. They give you the density of water. Okay, so this is kind of an easy problem, right? Because we know that the density is mass over volume, so mass is density times volume. So 1 times 10 to the third kilograms per cubic meters. And remember that when I use units, when I write them down, I put all the numbers to the left and all the units to the right, so I can work with the units and cancel and so on, okay? And then what's the volume of this cube? We have 0.025 meters, because you have to convert 2.5 centimeters is equal to 0.025 meters. And we have to square this because this dimension, this 2.5 is appears twice, times 0.035 for the height, right? And oops, and I also need meters cubed, which cancel. And if we carry on the calculation, we find 0.02 kilograms. B. All 6 compartments in the ice cube tray are filled with water to a depth of 3.5 centimeters. The ice cube tray is placed in a freezer. The initial temperature of water is 22.5 Celsius. It takes 12 minutes for all the water to become ice at 0 degrees Celsius. The manufacturer of the freezer states that the freezer can transfer energy at a rate of 110 watts. Evaluate whether energy is transferred from the water in the tray at a rate of 110 watts. They give you the specific heat capacity of water and the specific latent heat of fusion for water. All right, so what's going on here? We are losing energy due to the need to reduce the temperature of water from 22.5 degrees Celsius to 0. Okay, so the loss of energy can be calculated using the specific heat capacity of water times the mass of water times the temperature change. And then we also need energy to convert that water into ice, which will be equal to the mass times the latent heat of fusion. Okay, so that's 4,180 times the mass. We have all 6 compartments, so 6 times 0.02 kilograms, which we just calculated. It's actually 0.021. Okay, so I'm going to use that times the temperature change, which is 22.5 kelvins. Okay, don't forget that you actually have to convert to kelvins, but 22.5, but the same change in temperature in Celsius is the same as the same temperature change in kelvins. Okay, it's a special case. It only works for this example. Okay, and then we need to multiply the latent heat of fusion, 3.34 times 10 to the 5 times 6 times 0.021 like before. And hence we see that we need 56,503 joules. Okay, so let's find, okay, the question is evaluate whether energy is transferred from the water in the tray at the rate of 110 watts. Okay, so let's divide that with 10 minutes and see what the rate is. So 56,503 times 10 minutes times 60 seconds. So this gives us 78.5 watts. So no. And that's the answer, okay? It's less than 110 watts. I mean the rate of transfer of energy. All right. Okay, question 15. Doctors can use ultrasound to monitor the heartbeat of a baby when it is developing inside the mother. A baby's heart was beating at 142 beats per minute. I guess that's the frequency, okay? The wall of the baby's heart was moving with a maximum velocity of 22 millimeters per second. Calculate the maximum displacement in millimeters of the wall of the baby's heart. Assume that the motion of the wall of the baby's heart is simple harmonic. I think this is probably easier than it sounds. So the velocity is omega times the amplitude, right? So the amplitude is equal to the velocity over omega, which is equal to the velocity over 2 pi times the frequency, right? So we're given the velocity, which is 22 times 10 to the negative 3 meters per second. I'm going to write it over here. And then 2 pi, and what's the frequency? 142 beats. Okay, beats is unitless per minute, okay? And minute should go in the numerator. And to convert that minute, I mean, per minute, I mean, this is what I mean, right? But we need to convert a minute to seconds, right? So what's 1 minute in seconds? 60 seconds. Seconds cancel. And if we work this out, we find 1.5 millimeters. And let me make a short comment here. This makes sense, right? Because they tell you that the velocity of the heart is 22 millimeters per second. So your answer should be somewhere in the neighborhood of millimeters, okay? If your answer was 1 meter, right? Imagine how small a baby is. And if the displacement of the heart was 1 meter, it will explode, right? So yeah, I mean, in physics, sometimes you can logically infer whether your result is correct or not just by looking at it. I mean, just think of the order of magnitude and stuff like that. All right. Part B, the motion of the wall of the baby's heart only approximates to simple harmonic. State what is meant by simple harmonic motion. Okay. We can write the equation. I'm sorry. So A is minus omega squared x. Okay, so simple harmonic motion means, I mean, if you have to write it in words, the acceleration is proportional to the displacement, from equilibrium, okay, from equilibrium, and in the opposite direction. And this is what it means. All right. Question 16. A nucleus of thorium-230 is unstable, decays to a nucleus of radium-226 by emitting an alpha particle. The table shows the masses of the particles involved. Okay, that's good. Determine the energy in joules released when a nucleus of thorium-230 emits an alpha particle. Okay, so the what's going on is that we have thorium-230 going into radium-226 plus an alpha particle. Okay, what's the change in mass? Okay, we have 230.0331 atomic mass units in the beginning, right? And in the end, this converts to radium-226, so 226.0254 atomic mass units minus the mass of an alpha particle, which is 40026 U. Okay, so this is equal to 5.1 times 10 to the negative 3 atomic mass units. Okay, let me use a clean page because we are not done yet. We are actually asked for the energy released. So delta E is delta M C squared, our friend Einstein's equation. So we have 5.1 times 10 to the negative 3, and then one atomic mass unit is 1.66 times 10 to the negative 27. Right? I have a moment of doubting myself right now. Yes, okay, that's correct. Let's go back over here. Okay, times 3 times 10 to the 8 squared, and in joules this, wait, are we, yes, they are asking in joules, so this is 7.61 times 10 to the negative 3 joules. That's the energy. Okay, part B. Determine the time taken in years for 90% of the thorium-230 in a sample to decay to radium-226. And they give us the half-life of thorium-230 as 75,400. And from that we can determine the decay constant. Lambda is ln of 2 over T1 half. So I have to actually do it because I was a little bit lazy when I was going over this paper, I guess. So the decay constant is 75. Okay, so 9.19 times 10 to the negative 6, and that's years to the minus 1, which is okay to use that way, right? And now we can do n is n naught e to the minus lambda t, right? So we actually need n over n naught, which is equal to e to the minus lambda t, and I'm going to go back to the clean page. So if we take the ln of both sides, we have ln of n over n naught equals to minus lambda t. So the time we need to find is equal to minus, and then we have on the numerator ln of n over n naught over lambda. Okay, so we have minus of the ln of n over n naught is simply 0.1, because this is how many nuclei are left, which is 10%, because 90% is gone, so 10% is left, right? Over lambda that we just calculated, which is 9.19 times 10 to the negative 6 years to the minus 1 goes to the numerator and becomes just years, which I will write as y. Okay. And okay, so we have minus of ln of 0.1, which is 2.3, over 9.19 times 10 to the negative 6. So we find 250,553,553.3 years. Okay, let me see what I have in the notes. Okay, it's similar to what I have in the notes, so that's good. Okay, in the notes I just quote answers. I don't know why I was doing that. So I guess I was lazy. So anyway, let's go to question 17. In France, scientists from many countries are working together to build the International Thermonuclear Experiment Reactor, ITER. And as a nuclear physicist teaching, I guess, high school students, I have to say that this is a very interesting project to me. I wish I was able to work on it. I don't even know how to meet someone who works on this and express my interest. But for you guys that are young watching these videos, and I mean, for those of you who are interested in studying physics, this is, I think, an interesting direction to look into, because I guess the potential is enormous. I mean, they were going to study fusion from what I know. And okay, fusion, the joke I always tell my students is that fusion is always 10 years into the future. So in 1990, it was supposed to be 10 years into the future. Now it's 2026, and it's still 10 years ahead into the future. I don't know when that future will come, but maybe it will come in your lifetime. So it's worth exploring, big ideas like this. I always like big ideas, which is a double-edged sword, but I like it. I mean, I think it's an interesting project. So part A, on the ITER website, it states that fusion is the energy source of the sun and stars. In the core of these stellar bodies, hydrogen nuclei fuse into helium nuclei and release tremendous amounts of energy. Explain why energy is released when hydrogen nuclei fuse to form nuclei. So okay, the binding energy per nucleon increases when helium is formed. Okay. Hence, we have energy release. Okay. B. It is hoped that the ITER will be the first fusion device on Earth to maintain nuclear fusion for long periods of time. Another interesting project is, I think it's NIF. I forgot now. It's in California. Okay, it's the National Ignition Facility. Okay, and they try to do fusion using lasers. It's also an interesting project to look into. I think it's NIF. But okay, let's go to Google. Okay, National Ignition Facility. Is it NIF? Is this the name? Let's see. Yeah, it's NIF. Okay, I remember it correctly. Oops, that's CapCut. So yes, okay. This is another project to look into. Okay, to achieve fusion in the ITER, a hot plasma is used. The plasma must be at an extremely high temperature and have sufficient density for fusion. Explain why each of these two conditions must be met. So high temperature means high velocity and hence energy, right? High velocity means nuclei can overcome repulsion, right, and fuse. So nuclei fuse due to high energies. Okay, and we have to comment on the high density. Okay, so high density leads to a high collision rate, which means a higher probability for fusion. Okay. Moving on to part C. The graph shows the variation of binding energy per nucleon with proton number Z. In one possible fusion reaction, a nucleus of hydrogen-2 fuses with a nucleus of hydrogen-3. A nucleus of helium-4 and a free neutron are produced as shown in the following nuclear equation. Determine the energy in MeVs released when a nucleus of hydrogen-2 fuses with a nucleus of hydrogen-3. Okay, so we need to find the binding energies to begin with. Okay, so this is the nuclear equation. Okay, so binding energy. So hydrogen-2 is over here. It's this guy. Okay, and let me erase. So we have 1, 1.2, 1.4, 1.6, 1.8. Okay, so so this square represents 1 MeV, and the deviations represent, so this deviation represents 0.2 MeVs. Okay, so I'm trying to say that hydrogen-2 consists of two nucleons, one proton and one neutron. So, and one neutron, I'm sorry. So the binding energy will be 2 times 1.1. I mean, it seems like the binding energy per nucleon is 1.1 for deuterium, okay? And then for tritium, which is hydrogen-3, we have 3 times 2.8. I mean, it's kind of clear that the binding energy per nucleon is 2.8 for tritium, which has 1 proton and 2 neutrons. So 3 times 2.8. Okay, and this goes to 4 times, what's the binding energy? 7, right? It's a clean number. So the binding energy per nucleon for helium-4 is 7 MeVs. Okay, and then the binding energy of a neutron is ignored. I mean, there is no binding energy. It's a single neutron, right? So how do we find this? We are forming helium-4. So the energy, let's call it energy released. Okay, so the energy released is going to be 28 MeVs from helium-4 minus 2.2 MeVs from hydrogen-2 minus 8.4 from tritium. So the released energy is 17.4 MeVs. Kind of a strange problem, but this is the essence of binding energy per nucleon. You can actually use the binding energy per nucleon to calculate the binding energy, right? And if you know the binding energy, you can calculate energies released in nuclear reactions by subtracting the energy of the products minus the binding energy of the reactants, okay? It's kind of similar. I mean, it's the same in chemistry, right? I mean, this is what you do in chemistry. It's the same thing. So, not that I claim that chemistry is easier. I mean, I find chemistry actually hard, to be honest, okay? So, let's move to question 18. Wax is heated until the temperature is above the melting point of the wax. Okay, the hot wax is poured into a bowl and allowed to cool. The graph shows how the temperature of wax varies with time as it cools. Describe how the internal energy of the wax changes as the wax cools. You should refer to the energy of the wax molecules as the liquid wax cools and becomes solid, and the solid wax cools. Okay, times x and y have been included to help you refer to the graph. So we can answer this. So this is a long writing problem. As the wax cools down, okay, the internal energy decreases. okay, as the temperature decreases, the kinetic energy of the molecules decreases between x and y, okay, T is constant, so kinetic energy is constant, okay. As the wax solidifies, the potential energy decreases. The potential energy of the molecules decreases. And at y, the wax solidifies. And I'm going to write here that the internal energy is the sum of the kinetic energy plus potential energy of the molecules. And that's the answer. Okay, that's my answer. Let me see what they say in the mark scheme. You don't have it in front of you, but I have it in front of me right now. I'm just gonna read off what they say in the mark scheme. So, okay, so they say that the indicative content is that you should write that the internal energy of the wax decreases as time passes. We mentioned that, that's good. The internal energy of the wax, that's another point you can mention. The internal energy of the wax is the sum of potential energy and kinetic energy of the molecules. We actually just wrote this down, okay? As the temperature of the wax decreases, this is the third point, the molecular kinetic energy decreases. We mentioned that. Between times x and y, the liquid wax is solidifying and the molecular potential energy decreases. We didn't mention this, okay. And between times x and y, the temperature is constant, and so there is no change in molecular kinetic energy. Well, no, we actually mentioned this. We mentioned that the wax solidifies. As the wax solidifies, the potential energy of the molecules decreases, okay? And at time y, the wax has solidified. So, we covered everything that they want to hear. So, let's move on to question 19. It looks like a scary arrangement there, okay? Let's see. A student hangs a mass of 0.22 kilograms from two identical springs as shown. She displaces the mass vertically and the mass oscillates with simple harmonic motion. The student measures the time t for the mass to complete 30 oscillations. She repeats this measurement. Her measurements are given in the table, okay, T1 and T2. The springs are taken from a box labeled K equals to 21 newtons per meter. Deduce whether the value of K stated on the label is correct. So, this is a strange question. So, let's start with the period. Period is 2 pi times the square root of m over k. So, t squared is 4 pi squared m over k. So, k is 4 pi squared times m over t squared. Okay, so T30 for 30 oscillations is T1 plus T2 over 2. Actually, let's name this T for 30 oscillations. And this is the average. I mean, I'm trying to find the average. Is 13.68 seconds. Therefore, the period is T30 over 30, right? So 0.46 seconds. Let's use move to a clean page. So the K is 4 pi squared times the mass, which is, where is it? 0.22 kilograms, 0.22 over the period squared, so 0.46 squared. So we find 41.8 newtons per meter. So we have to divide this by 2 because when you have two springs in parallel, K adds. Okay, so if this is K1 and this is K2, then K total is K1 plus K2, in this case just 2K since they are identical springs. Okay, so if we divide by 2, we find 20.9 newtons per meter, which is about 21 newtons per meter. So that's okay. I mean, the claim is correct. Right. Part B. The student attaches the mass to one spring and holds the other end. She sets the mass into oscillation by oscillating her hand vertically as shown. The student increases the frequency at which she oscillates her hand. She keeps the amplitude of oscillation of her hand constant. She observes that the amplitude of oscillation of the mass increases to a maximum and then decreases. Explain this observation. So resonance occurs, okay? So a resonance occurs. Okay, so the frequency of the driving force equals the natural frequency of the spring. So we have a maximum transfer of energy. Okay, and we are left with the second part of question B. So the student makes the following conclusion: as the frequency is increased, the amplitude of the mass increases to a maximum, so energy conservation does not apply to this situation. Okay, so the way to answer that is that when the amplitude is a maximum, okay, maximum energy is transferred to the surroundings. Okay, and also some of the energy from the student's hand is transferred to the oscillating mass, to the mass, but also the surroundings and the surroundings. Okay, I will need a clean page. However, in a closed system, energy is conserved. Okay. Therefore, the student is wrong. In a closed system, let's write the total energy. So the total energy is conserved, therefore the student is wrong. In other words, all the energy from the hand goes to the mass plus the surroundings, okay? That doesn't mean that energy is lost. I mean, the conservation of energy is always valid. All right, question 20. The Hertzsprung Russell diagram for a star cluster is shown at a scale to the horizontal axis. Okay, so the energy is increasing backwards. Okay, you have to remember this detail. So let's say that this is about 2500 kelvins. The next one is about 5000. Actually, where the sun is about 5000, okay? And the sun is at 1. The luminosity over the luminosity of the sun is 1 here, so the temperature is about 5000, actually 6000, but okay. And the next one in the scale should be 10,000 Kelvin, and the last one should be 20,000 Kelvin for these guys up there, okay. Part B, explain how this Hertzsprung-Russell diagram shows that the star cluster is not a young star cluster, okay. You should refer to the groups of stars and their positions on the diagram. Okay, let me erase these lines here, okay, so that we see clearly. All right, okay, so the answer is that in the top right over here, so top right, we have many red giants. Okay, we also have lots of white dwarfs over here. So bottom left, lots of white dwarfs. Okay, and what else? If the cluster was young, we would have only main sequence stars, which is not the case here. Okay, in other words, we will only have stars in that diagonal, which is not true. I mean, we have many stars off diagonal. Okay, so let me remove that. Okay, and let's move on to part C. In the early 20th century, Edwin Hubble observed the Andromeda Nebula. He saw stars similar to the stars in our galaxy. One star he saw was a standard candle known as V1. Describe how measurements of the standard candle could demonstrate that the Andromeda Nebula is not a nearby star cluster. Okay, so standard candles have known luminosity. Okay, let's call it L. So we can measure, we can measure their intensity I, which is equal to the luminosity over 4 pi times their distance squared. So we can measure their intensity I on Earth. And using the known L, we can find D, which is simply equal to the square root of L over 4 pi I, right? All right, so if we do that, doing that will show that D is very large. Therefore, the Andromeda is not a nearby cluster. Okay, and that's the answer. Let's move to question 21. Ross 154 is one of the closest stars to the Sun. The graph shows how the power radiated from Ross 154 depends upon wavelength lambda. I wonder if it is named after that painter. He has lots of videos online. I think he passed away long ago, but his videos are very popular about drawing stuff. So anyway, I don't know why the name is Ross. So anyway, let's move on. Show that the surface temperature of Ross 154 is about 3000 degrees Kelvin. Whenever we have a diagram like this, we have to think of Wien's law. Okay, so this is what we will use here. So the peak lambda times the temperature is 2.98 times 10 to the negative 3 meters Kelvin, and the peak lambda here, and the peak lambda means the wavelength at which the radiation power is maximum. So this thing over here, okay? And if you go read it, that's about 880 nanometers. So the temperature is 2.98 times 10 to the negative 3 over 880 times 10 to the negative 9. So we get 3386 Kelvin, which we will call 3000 Kelvin. So it's about, I mean, our answer is close to what they ask. Okay, let's move on. Part 2. A website states that the luminosity of Ross 154 is less than 0.5% of the luminosity of the Sun. Evaluate whether this statement is correct. They give you the radius of Ross and the luminosity of the Sun. So L, the luminosity of this object, is sigma times 4 pi times its radius squared times the temperature to the fourth. And I'm going to be lazy and just quote the result, which is 1.3 times 10 to the 34 watts, okay, which is equal to 0.34% the luminosity of the Sun. So the statement is actually correct, okay? And part B, which is the last question of this test. Scientists have observed an Earth-type planet in orbit around Ross 154. The radius of the orbit is 0.096 astronomical units. Calculate the time for this planet to make one orbit of Ross 154. And they give you that 1 AU is 1.5 times 10 to the 11 meters, and the mass of Ross is that. So, all right, let me think. We need to find the period, right? So how do we do that? When a planet goes around a star, I guess, it experiences the gravitational force given by Newton's law, g times the mass of the object times the mass of the planet, which I call lowercase m, over r squared. And that force provides the centripetal force for the object to stay in motion, right? Around the star. So, and this is equal to m omega squared times r. M goes away. So I'm going to use a clean page again. So you always have to prove this, unfortunately. So gm over r squared is 4 pi squared over t squared times r. So t squared is 4 pi squared r cubed over gm. So t is the square root of this thing. So 4 pi squared r cubed over gm, okay? And if you plug in numbers, you find 2.29 times 10 to the 6 seconds, Okay, and that's the answer. Okay, this was the Unit 5 test from June 2023. I hope this is useful. Let me know in the comments if you have any questions. I'm sorry I kind of rushed this. I went over questions a little bit fast, but hopefully I was clear and I didn't confuse you. And please like and subscribe. If you want to support the channel, I'm gonna be grateful. I have a PayPal link. And see you in the next video.